The next gas power cycle that we want to take a look at is that of the internal combustion engine, but with compression ignition, not the spark ignition process that we looked at for the auto, but this is the compression ignition. This is referred to as being the diesel cycle, and we will look at an ideal version of the diesel. So the diesel is sometimes referred to as being constant pressure combustion. And we'll see that when we look at a PV diagram, why we would call it a constant pressure combustion process. So let's take a look at our PV diagram. And the diesel is similar to the auto with one exception, and that is the way that we do the heat addition process, or where the combustion actually occurs. So we start off and we're at bottom dead center, just like we were for the auto cycle. So we'll be at state 1. Now what we do with the diesel is we go through and we have a much larger, greater compression ratio than we did for the auto. And consequently what happens is the air, now we do not have fuel, it's only air that is being compressed, goes to a higher temperature and a higher pressure. And that is when we're at top dead center. And then what the diesel does is that is when you inject the fuel at that point. And given that we're at such a high temperature, that you will then get the combustion process taking place because of the high temperatures. And so you're injecting fuel at the end, and then you begin to expand. So you're at top dead center, you've compressed, it's at a very high temperature, you inject the fuel, it then starts to expand. And we can then refer to that as being constant pressure expansion. Again, that's a bit of an approximation, but we'll approximate it to be constant pressure expansion, taking us to state 3. So this here is where we are doing our combustion, with which, if you recall, we model that as a heat addition process. And then we go into another isentropic process, and that is an isentropic expansion, just like we did in the auto. And so we come back down to state 4. From 4 to 1, we do heat rejection, which is basically exhaust. However, it's modeled as a cycle, so really we don't dump the gases out, but we will model it as heat rejection, but really it's the exhaust cycle. So this is isentropic compression here, and this is isentropic expansion, or your power stroke. So that is the difference between the auto and the diesel. It's mainly with what's going on here with our heat addition process. So if you recall when we talked about the auto cycle, we said if you have too high of a compression ratio, you could have auto ignition or knock, pinging in the engine. Here, although if you listen to a diesel, which I'll show you in the next video, it does make a lot of noise and it does sound like a bit of a pinging. But here what we're doing is we're injecting the fuel after, and that is what starts the compression, or the combustion process. So we do not have the auto ignition or the knock problem, I guess you should say, because we do have auto ignition. We don't have knock that you would with the auto. Another parameter that we will use when we look at the thermal efficiency for the diesel is that of the cutoff ratio. So I'll write out the cutoff ratio now. So the cutoff ratio, remember before we had the compression ratio R. Now the cutoff ratio is little r subscript c, and that is the volume at state 3 divided by the volume at state 2. Given we're dealing with a closed system, same mass, we can write the specific volume of 3 to 2. So that is the cutoff ratio, which we will use when we come up with an expression for the thermal efficiency of the diesel cycle. So let's take a look at that now. In doing this, what I'm going to do is I'm going to look at the heat addition process, so basically going from state 2 to 3, and I will also look at the heat rejection process going from state 4 to state 1. So what we'll do is we will express the first law for both of those processes, and then we'll work through it and come up with an expression for the thermal efficiency of the diesel. So for the first law, what we want to look at is 2 to 3, which was our constant pressure combustion or heat addition process. So writing out the first law, now we have this term here, boundary work. When we looked at the Otto cycle, we were able to reject that because it was a constant volume combustion process. We no longer have constant volume combustion. When we're going through the heat addition, we're actually increasing the volume, and consequently we're doing boundary work with our fixed mass system. So what we're going to do, we're going to make the substitution or the change that we saw when we looked at the first law for closed systems, and that is you can encapsulate the boundary work with the internal energy and re-express it as enthalpy. So let's do that, and we can write Qn is equal to the enthalpy change. So now we're taking into account both internal energy and boundary work, and we can then rewrite that if we assume constant specific heats. So that is our first expression. Now looking at process 1 through 4, there we have Q out, and remember our designation was that Q in is positive for this system. If it's out, it's minus, so that becomes a negative. Minus the work is equal to the change in internal energy between states 4 and 1. Now here it is at constant volume, and consequently the boundary work term disappears, and what we're left with then is Q out equals U4 minus U1 minus Q out. So we can take that now and we can plug it into our expression for the thermal efficiency of a diesel. So we have that, and now what we're going to do, we have an expression for Q out, and we'll plug it in there, and we have an expression for Q in, and we'll plug it in there. Now the thing that I should say about the Q out, this was U4 minus U1, we can substitute that as CV T4 minus T1. So again, we'll be able to plug in an expression in terms of the temperatures. We don't like that. We like to have it in terms of the compression ratio, so we can rearrange and get to one with the compression ratio. But let's take a look at what the thermal efficiency of the diesel is. So the thermal efficiency of a diesel cycle, now this is an ideal because we're making approximations about the specific heat not changing. And if you notice, so we have this part. This is the exact same as the Otto, but now it is modified by a term in square brackets that has the cutoff ratio embedded within it. R is our compression ratio, RC is the cutoff ratio, and K is the ratio of specific heats. So this is identical to what we had with the Otto with the exception of this term here. And it turns out that that term in square brackets is actually always greater than or equal to 1. And with that, what it means is that the thermal efficiency of the diesel is always going to be less than that of the Otto. According to this expression. Now that might be surprising because some of you may be aware that diesels get better fuel economy than the Otto. So how can it be that the diesel has a lower thermal efficiency than the Otto? Well, the place where we're able to correct for this is the fact that the diesel is operating with a much higher compression ratio, and consequently we can get higher thermal efficiencies for a diesel. Diesels tend to be somewhere in the ballpark, depending upon the design of the engine, in the 30 to 40% ballpark, and consequently it is a higher thermal efficiency than we saw for the Otto. The other thing is, given that the diesel is compression ignition, you can combust or burn a lower quality fuel in a diesel, and consequently, theoretically, it should be cheaper. Although some parts of the world, diesel and standard gasoline, there really is not that much of a significant difference. But in terms of upgrading and refining and everything, the fuel should be a little cheaper economically. So that's the diesel cycle. What we're now going to do is take a little bit of a look at the compression ratio, and then I'll show you a quick video of a diesel operating, and you can compare it back to the Otto, where you'll notice there's significant difference in the sound of the two.